Nisa. How
Hi,
are you?
hi, good. How are you doing?
I'm fine, thank you.
Yep. Yeah, thank you for joining us today.
Nice to meet you.
So, สวัสดีค่ะอาจารย์มนต์สิทธิ์ค่ะ
สวัสดีครับ
สวัสดีค่ะอาจารย์สวัสดีค่ะอาจารย์กากค่ะ
สวัสดีครับ
สวัสดีค่ะ
สวัสดีครับพี่เปิ้ล
สวัสดีค่ะเบรน
ครับ Hi Good evening and good morning
Brin, how many are we expecting?
At least 15
Oh, okay. I think we surpassed that.
Yeah
We have uh 32 now.
Okay
Yeah. Good evening. I can name.
Good evening everyone
Good evening, good evening. So great to see you, everyone.
Yeah. Okay. Maybe. Hi.
Oh, good evening or good morning.
Hi, Darren.
Hello.
Mm. And hi,
Hi,
Professor.
how are you?
Yeah, good. Mm. Yeah, you must be busy, right? You have some festival lately, right? In Kazakhstan,
Yeah,
right?
some part of our team, not me.
Okay. I will be waiting maybe until 7:05. Okay, because actually I think most of us are here, but I would like to make sure that every participants most of them are here. So let us wait for another maybe 4 minutes. Yeah. And how do you would like to show the slides yourself? Am I right?
Yes.
Yeah, so you will you can try share the screen while we are waiting for participant. Yeah, we can check on your slides.
Sounds good.
Yeah.
Can you see those?
Yes, we can see. Yes, we see the slides clearly. Okay, yeah, that's great. Yeah, and you sound clear to me.
Okay.
Yeah.
Well, if there's any questions or if I'm not clear, I'd like this to be interactive, so feel free to jump in with questions either in the chat or put your hand up. And
Yeah.
if 2 page, if I don't see, if someone can just jump in and say, hey, I have a question.
Yeah, that sounds great. And in 2 more minutes, we will start, and I would like to maybe introduce later about who are attending today, right? Because there are more participants from the STEP program. Okay, but yeah.
What?
I can't remember how to go into chat.
There is a icon at the bottom that's the chat icon that you can click.
Yeah, it's not the chat. I forgot to put how to put people into breakout rooms.
Oh.
I had to teach online for over a year, and so I try to put that out of my mind.
Do you mean the session, when you can break the rooms, right?
Yeah, in Zoom, actually we can, but I'm not sure about this one. Usually it's the organizer will be the one who do
Yeah,
it.
I can assign you as a co-host, then you can set up the breakout room.
But for the breakout rooms, if you would like to have like, if we do not preset, they will randomly assign. Am I right?
Yeah, this I'm
Right.
not sure. Maybe have to
Right.
manually assign them.
มงคล can มงคลถูกไหมฮะ ถ้าเราไม่ได้เซตก่อนล่วงหน้า มันจะ random ใช่ไหม
They're talking about.
We have
ใช่ไหม
I already make and the co-host, so you have the same control as host now.
Yeah. I would like to check with มงคล am I right มงคลใช่ไหมคะ ถ้าเราไม่ได้ preset มันจะ random ให้ใช่ไหม แล้วมันต้องบอกว่าต้องกี่คน
มี3 แบบพี่ครับ ทั้งแรนดอมทั้งแมนนวลเข้าหรือเราเซตติ้งให้ครับ
แล้วเกิดถ้า
สามารถทำได้
click breakout room ไปมันจะเจออะไรคะ
อยู่ที่เราตั้งจำนวนห้องครับ ว่าจะตั้งกี่ห้องนะครับ แล้วก็วิธีการเข้าแบบไหนนะครับ
Okay.
มาคอนโทรลได้
Yeah, and are you going to break out, like set up the breakout rooms later, or you think today mostly?
So I was thinking a couple of times just to randomly go into breakout rooms for a few minutes in small groups and then come back. Is
Yeah.
that something that you can do for me or something that I would do?
Yeah, depends. Like if you click the breakout rooms, or we can do it for you. You would like how many rooms that you set up?
It depends how many people. We can get 4 or 5 people in a room.
Yeah,
At,
so 10, yeah, maybe 10 people in, yeah,
breakout rooms.
yeah, like 10 rooms, right? And then each have 4 people.
That would be great.
Yeah, Mongkon, so how about this? I will ask Mongkon to help. So Mongkon can randomly break
Okay.
session into 10 rooms.
So I see it right now on mine. Yeah, create 10 breakout rooms, just assign.
Yeah,
So I can do it or you can do it, either one.
yeah. So you can say, okay, now go to breakout room and my people can help so that it will not distract you so much.
Okay.
How about that?
Okay.
Yeah.
Sounds good.
Yeah, Mongkon can stand by นะคะ
Yes I'm standby.
Okay, that's great. Right. Yeah, okay. I think now we have about 40 participants, right? And then I would like to say good evening and good morning to Professor Joe and Dr. Ann. So welcome to the webinar series on STEM education. This series is part of 2 initiatives. One is under the STEP program. We have to rename the program to avoid the duplication with the other center, Simeo Regional Center, to be CTEP, Southeast Asian Teacher Education Program. So from now on, we will call our program CTEP, not STEP, right? And the other initiative, we invite participants from other countries as well, so that they can benefit from the webinar series that we are organizing. And we also expect that they can, besides learning or exchanging ideas from this webinar, they will also have a chance to implement the units at their schools or at their universities. So new participants that the CTEP program participant might not know, they are from the invitation that we extend to. And we thank you for your interest to join in this webinar. And as you might have heard that we also have a small grant to those the schools that who want to implement. But for the CTEP program, we will direct the grant to the implementing agencies so that the support can be provided directly by the implementing agencies. So yeah, we thank you for your interest, and it's an honor that we have Professor Joe and Dr. Ann being with us, and this program is supported by Chevron Corporation. Without their support, it will not be possible to have this event because of the funding that they kindly grant to Senior STEM Ed. So we appreciate their support on this. So I would like to start with an introduction of Professor Joe Kraychik. Professor Joe, could you greet with the
Hi,
participants?
everybody. Can you, because Ann and I are in the same room, so I have my volume off. So can you hear me okay?
Yes, we hear you clearly. Yes.
Welcome, everybody. I'm Joe Kraychik. I'm a professor of science education at Michigan State University, and I've been working with Kesra in Thailand for several years now, and I enjoy my work.
Yeah, thank you, Sir Joe, and Dr. Ann, please.
So hi, everyone. For those of you I've met before, it's nice to see you again, and it's nice to meet new faces. I am a middle school science teacher, and I developed this curriculum for water, which I'll be sharing with you over the next several times. And I'm very honored and pleased to be with you.
Yeah, thank you, Dr. Ann. So from our team, we have my team member, Dr. Burin, please.
Hi, good morning and good evening. So I'm Burin Asawapipok. I'm the one that who sent an email to you. So if you have any question, just inform me. Thank you.
Yeah, and I have my support team member, Mongkon. Please show your face.
Hi everyone. Good to see you again about the workshop. Yes, see you. I support everyone. Thank you.
Yeah. So this webinar is part of the series that Dr. Ann will be conducting on the topic of water quality, and it's based on an open source learning unit that Professor Joe has kindly introduced to our program, and also please feel free to use them because it's open source, and we believe that introducing good learning unit that helps students in the scientific explanation using the claim evidence reasoning that Dr. Ann will be introducing to you today will be a good instructional practice that teachers can introduce in a classroom. And along the way, there will be more workshops related to the modeling. That is also part of the key practice that we want to introduce to teachers to use in the classroom for students to make a meaningful scientific explanation. So yeah, I hope you enjoy. And Dr. Ann, the floor is yours.
Okay, thank you. So again, good evening, and thank you so much for coming on a Saturday night. So I understand that's a valuable time, so I appreciate it. I do want this to be interactive, so if you have questions, just unmute and jump in. I'm not so good at staying up with the chat, so if there's something in the chat that I don't see that's a burning thing, please, call out. I'm going to be talking two ways. One with a teacher hat, so I may be addressing you as middle school students, and then of course in terms of how we go about teaching our pedagogy and our instructional strategies, as adults. Okay, so can everyone see my screen? Okay, so what I have developed is a unit, how healthy is our stream for freshwater organisms? And then also, how do our activities outside on the land negatively impact the stream? So my goal is to really help students develop a deep understanding so that they have usable knowledge of a really complex stream system. And so they're going to engage in this phenomenon, and it's a project-based learning environment. I sent you the link, but what I'm going to be doing is I'll be going through some parts of the unit. We'll take a look at the link, the teacher materials, off and on throughout today and other days. Why doesn't it move ahead? Any idea why it's not moving? There we go. Okay. So one of our goals as teachers, or actually our major goal, is to really create learning environments that move away from students just memorizing science ideas. Because there's a lot of research that shows if students just know science ideas, but they don't know how to use those science ideas, that they really don't have a deep understanding. And so our goal as educators is to shift, to make a paradigm shift where we're exploring and explaining phenomena. And in that process, students are going to develop deep understanding of important science ideas, but they're also going to engage in the same practices as professional scientists. So the water unit is flexible. So it's written kind of as a choose your own adventure with some important things that hopefully everyone will engage in. But what teachers can do is they can adapt the unit and personalize it based on their situation. So if they have easy access to water, or if they don't have easy access but have water nearby that they might be able to make a trip or two during the unit, or if they have no access to water, this unit allows teachers to actually bring in water samples from a stream or a river. The other thing, it's flexible in terms of technology, right? So some schools may have a lot of technology tools and equipment, and other schools may have less. So there are suggestions in the unit on types of equipment that can be used. And the other part of flexibility is the amount of time. So at my school, I do an entire 1 semester unit. This unit is written more like for 5 or 8 weeks. And I'm happy later on to share more of the things that I do, but this one's a shorter unit. So this is just a quick overview of science and engineering practices that are part of the unit. In the middle, you'll see the science ideas. And then on the far right, these cross-cutting concepts that really will go through any discipline. There are a total of 7 of them that are in the new framework for K-12 science education in the US. In this water unit, 4 of them are really focused on patterns, cause and effect, systems and systems models, and stability and change. And I assume, Kessler, that all these slides are going to be shareable, right? So is that the case?
Yes, I think, yeah.
We'll link the slides. This is also like a unit organizer. And today we're going to talk a little bit about hopefully the first 3 lessons and maybe 4. And then you can see that there's arrows that go up and down. So the top, the colored boxes on the top are talking about models, and the ones on the bottom are talking about explanations. Today we're not going to go in depth on those because you're going to be meeting with Joe sometime this week, and he's going to be introducing at least explanations or models too.
I think both.
Okay, so once he does that, then when we come back, either the next day or the other one after that, we're going to be connecting this unit with those. And a book came out, Science and Engineering for grades 6 through 12, in terms of how teachers can support investigation and design. And One in particular, well, there's several I'm going to share. The phenomenon or challenge needs to provide more than just a hook to interest students, but it also really needs to spark a lot of questions that can be used to drive learning and through investigation and design. It's really important to contextualize real world phenomena. And so in the yellow here, this idea of having real world phenomena for students to investigate, that's the overarching and unifying driving force. So in in all the activities we do it in science, this is something that should really drive our instruction. And then either real world phenomena or human challenges really should be the heart of students' engagement in science, investigation, and engineering design. This notion of really authentic contexts, and then choosing a phenomena that's relevant to the community is also going to be relevant to students, and it needs to be sustained over a period of time. And then lastly, really the importance of choosing phenomena that's relative to students, and that isn't just important and they're interested in, but it really has to have important science ideas, right? So we're not just engaging kids in things that are fun and they're interested in, but really it's in the service of kids developing deep understanding of science, but that science can be investigated. I don't know why. Okay, there we go. So the water unit really fits all of that criteria. So we have a complex phenomena. It really needs to be explored over time in order to develop an understanding. It's not something you can really learn in a week or two. And so it has a lot of sustained investigation for students. And in this process, they're going to ask questions. They're going to be able to investigate cause and consequences, and they'll be collecting and analyzing up to 5 pieces of data. And they'll develop 2 things, scientific explanation and or create models. So there are 5 sub-questions. The first is the stream acidic, basic, or neutral? Where we'll be looking at the pH. Is our stream too warm for fresh water? That's looking at thermal pollution. To support life? And then are there too many floating particles? So these are everyday kinds of questions that middle school students can find engaging, that really then each one will help students to develop a richer, deeper understanding of the stream system as a whole. Okay, so for each water quality test, there's a student reader. I believe that you got an email, or you will get an email that has all of them. They're also in the unit, but what I sent you is the whole pack. There's 5 of them. And these materials are written for middle school students that engage them in developing understanding of the background knowledge for each test. In the unit, there are suggested uses for those. But the whole idea in terms of creating in learning environments is to try to do more guided inquiry and less focus on telling. That does not mean there'll never be some direct instruction, but in general, really trying to get students to be the ones who are engaging in materials and activities to develop understanding. Okay. So the first lesson we ask, why do we even want to study water quality? So this lesson can set a context, and it can be 1 or 2 days, or it can even be up to 2 or 3 weeks. For me, I spend several weeks doing contextualizing activities that not only set the context, but also have important science ideas. The goal is to really motivate and to create interest, kind of a need to know. It's going to situate all the groundwork for the driving question, and it's going to help students not only understand the importance of the question, but also to help them see themselves in the unit. So in terms of setting the context, it really can't be underestimated, because students really need to be invested in their learning. We want them to be active learners, not just passive learners. We want them to take ownership of their learning and to become student-centered, so they can actually see themselves in the unit. So they're part of what's going on. It's not, I'm learning about this on the side. It has nothing to do with me, but this is something all about me, and it's important for me and my family and my community. And so how that can be accomplished is by really finding an engaging phenomena that both has really important science ideas, that's the stuff we want them to learn, but that can be investigated. So it combines doing the practices that professional scientists do, that engages them also with the science ideas. So I start out the unit and ask, what are some questions that we can ask related to water quality of fresh waters and people? So after I do some contextualizing activities that include learning about, sharing a little bit about water, I have them generate questions and put them on sticky notes. And oftentimes kids really don't know that there's questions they have yet, but after we do some contextualizing activities, often there's lots of questions that spark their interest, and so they're curious, and we put them on sticky notes. In my classroom, we have 6 classes of 7th grade students. I teach 4, and my colleague teaches 2. And what we do is we have different classes put sticky notes up on cupboard boards, and so we know each class that has their questions. Some other people create question boards. It's really nice that students put their questions up and we share questions, and then over the course of the unit, we can go to that board and say, oh, a student asked this question, can we answer it now? There's nothing that creates more excitement for students to know that that's their question that they asked, and we're now able to answer it. Why do we really want to study water quality, and how do I contextualize learning? So back in the summer, I went through all the or many of the contextualizing activities that I've done. I'm just going to summarize them here, and then Kesra or other people, if you want more ideas of what I do, I'm happy to do that, like in the next PD. But since I really want students to take ownership, I really start, like, what are students' ideas right now? So I always ask them, what do they know about water? Or what do they know about anything we're going to be looking at? What I found, and I've been teaching this unit for over 25 years, is that students actually know very little. They know the water cycle because they've already learned that, but they don't really have any idea about water quality. But it's really important to see where they're at now so that you can build from that and connect with that. We do activities to look at how much water is on Earth and how much is usable for our everyday activities. Because of the 70 to 75% of the Earth's surface covered with water, less than 1% is actually available for people. Our students do a home water family usage survey. I have them predict how many gallons of water they use in an average day. And they'll say things like 10 gallons, 15 gallons. And so they do a survey with their family to see. In the United States, it's embarrassingly wasteful, all the water that we use. And you might want to have your students do that and make a comparison of the average family in the United States. But we also really think it's kind of foundational for kids to get an introduction to watersheds. We do a physical model, and then we also focus in on point and non-point source pollution. And again, I would be happy on another day to share more of that. Okay, so this is something that I sent to all of you. It's actually not in the unit, but one thing that I talk about with students at the beginning, but then we make connections to it throughout the unit. So I ask them, after we introduce point and non-point source pollution, I ask them to circle a potential pollutant, name the pollutant, and if it's point or non-point source. So they can circle this, and they can put a thing here, and they can put fertilizer. My handwriting is terrible, by the way. And it's even worse here. Okay, so they can put fertilizer. And then we ask, is that point or non-point? And if they have an understanding, they'll say non-point. And this introduces this idea, along with watersheds, that you don't even have to live close to water. Let me find my button here. So this is the water right here. Right here's the water. You don't even have to live close to water to have runoff go into it. It's a concept that students really don't understand. They don't even understand that they actually live in a watershed, because the water hits their house and it runs off. So, so these simple concepts that we could take for granted, kids just don't have an understanding. It's a fairly simple concept, so they grasp it fairly easily. But this notion too that things can happen underground if there's leaking gas that can end up in waterways. And so there are, you know, the focus on this unit is what people do on the land that can impact the water. And so there's a dual purpose, actually. I want to engage kids to become global eco-citizens, and that they have a responsibility to try to keep our environment healthy, and in particular for this unit, for water. Okay, so move on. Okay, whoops, I need to get rid of that.
Hi, Anne.
Yep.
May I ask, what the difference between point and non-point? What do you mean by that?
So point source pollution is pollution that comes mainly from a factory, where a factory has a pipe that connects directly to the stream. So I'm trying to go back. How can I go back? I want to go back to the last slide. There we go. Okay, so wastewater treatment plants, for example, when they, let me get a thicker slide here. Okay, so this is a wastewater treatment plant here, and it has a pipe, and it discharges. So it takes dirty water and cleans it, and then it pours that hopefully clean water back into a waterway. So wastewater treatment plants are situated near waterways. Here's a factory here as well. And in this picture, right, so there's a pipe that connects. So there's two things that can happen in terms of factories. One, they can make products, and they're supposed to make sure that any chemical waste doesn't go into waterways. So in the United States, in the early 1970s, they passed the Clean Water Act to tell factories were just dumping chemicals, and the waterways all across the United States were really getting polluted. And so the Clean Water Act said to factories, you can't do this anymore. You're going to get major fines. And it really decreased point source pollution. Now some of those rules aren't enforced, so it's not as good now. But so point source pollution, you can pinpoint it. It's very easy to find. So this pollution here, if you're doing water quality testing here or something and you see, oh, this chemical is coming here, you can go right up into that pipe and see that, okay, it's definitely connected to that factory. For non-point source pollution, it usually comes from runoff. And so you can't pinpoint. So if there's fertilizer that comes into the water, bless you, into the stream, we don't know if it came from this factory, from this farm or another farm, or if it came from my garden, right? So you don't know the source exactly. The other thing about this diagram is, so it introduces students both to a whole slew of potential pollutants, and then also shows, so this here is underground. So you can see how things can get in through underground pollution. And then the other non-point source pollution could be acid rain, because we don't know, like, so in the United States, we live in the middle of the country in Michigan. The people on the East Coast who have issues with acid rain, they kind of blame us. They said all the industrial, there's a lot of industry in the Midwest, and they think that the pollutants there then get blown and become acid rain in the East.
I see.
So
Thank you. Yep, thank you.
Thank you for jumping in with a question, and please make sure to do that because I can't see, I can't see all of you. Okay, so now, I'm having trouble moving my slides forward. There we go. Okay. So I think it's really important when you do PD with your teachers that you let them, this is really important, like what context are they going to create to anchor instruction? So again, for me, I live in Michigan. We're surrounded by the Great Lakes. So we have 20% of the fresh water in the entire world right in our backyard. So you would think that we shouldn't have any water issues, but unfortunately we do. And a few years ago, Flint, you may or may not be familiar, Flint is a city right in the middle of Michigan, and they had terrible water quality and they had awful looking water coming out of their faucets, and kids got lead poisoning, and it was a mess. And there's still problems with it, but we have problems all over the state with water quality and fresh water. So if teachers have time to find examples, articles, YouTube videos, what activities they're going to do, so to get them started helping kids understand the importance, not scaring them, right? So there's lots of horror stories I could share with them. I share some, but the idea is not to scare them, but to show them how important this issue is. So I let them, I would encourage you to have your teachers spend some time with that. Okay. Then once you're going to introduce the driving question, as I already said, various options. For me, I am so lucky. I have a stream that runs right on my school property. So I can go to the stream anytime I want. So within my class period, we can go out, we can come in. But for other people, it's just not going to be that close. So when I introduce the driving question, I take my students on a walk and we walk to the stream. But other teachers can pull up a picture or a video, somehow the way they're going to introduce the stream. So there's a lot of options for that. Okay. Then I ask my students, okay, so we want to investigate a stream, but how will we know if our stream is healthy or not? How will we know? And it's interesting. I put them into groups. I ask them, what do they come up with? How are we going to know? And one of the more common ones is they say, we can drink the water. Well, I think that I have had to be very clear that this unit is not about drinking water, but it's about water quality for fish. And this is something that students can get confused about because they're naturally thinking about themselves, right? They're middle school students. And so This is a hard one. They don't know. And maybe someone will say, I don't know, we can do some tests. That's not very common for me to hear. But they might say, we can look at it, we can smell it. So it seems to me then the next question that I say, if someone says we can test it, I try to guide them to say, maybe we should first look to see what the experts do, right? Find out how experts determine water quality and see what tests they do, what tools do they use, what do the tests mean. We can talk to our local experts or have them come in. And so what I have them do is just spend 10 minutes doing an internet search, looking at what experts do. And I stress that they don't need to understand any of it. And mostly they don't, they're familiar with temperature, but we're just trying to get a list of everything that we can do. And what we find is we get a list of however many things they find, 15 or 20 things, and I circle anything that we can do. And then I also introduce the difference between quantitative and qualitative data. This is so empowering for students to see that we can actually do what professional scientists do. It's probably the most common feedback I get at the end of the unit, how students thought it was so cool that we could do the same thing that a professional would do. And then we say, then, are there any new questions for the driving question board? And now there's lots of questions because they have a list. They're like, what is pH? What does it mean that you're looking for clarity? You know, what is dissolved oxygen, right? And so they're excited. They have lots of questions, especially since we circle that we're going to do most of them. And so it generates a lot of enthusiasm. Okay. So then we start our first water quality test, which is pH. And again, I ask, when you hear the term pH, what do you think of? And I first have them jot down some ideas individually. Most of them have nothing to jot down. I ask them to talk with a neighbor and then we share. The most common thing students have heard about pH is in their fish tank. They don't know why, but they know they have to do something about pH. They might know that they see a lifeguard at a swimming pool do some tests. And I said, one of those is pH. If they have a hot tub, they must say, we have to like test for pH in our hot tub. That's the extent, although a student or two might know something about acids. Oh, I think it's about acids. And so what it does though is it creates this need to know, okay, so we need to find out, first of all, what pH is, and then we also need to find out in terms of water quality. Okay, so I sent this to you and I'm going to put it up here and 1 second. I actually laminate this for my students. So I have like about 30 of these in my class. And what I ask them to do, and in a minute, I'm going to have you go in breakout rooms. Instead of me saying, oh, here's a chart, let me explain it, I say, here's a chart. And what I want you to do in groups is to study this chart from top to bottom, from left to right. Whoops, something's missing on this chart. Do you have the one I sent you? There's something missing, I realize. This part here is missing. But if you find the one do they have the chart? Did they get it emailed?
Yeah, I already sent
Okay.
the link. Let's include all the material for that you sent.
Okay, great. So I asked them to write down everything they can learn from this chart. Now, this is a nice skill, right? Because it seemed my experience when students read science materials, they only want to read what's in the text. They don't really look at the diagrams or they don't really study the diagrams. So I'm going to ask if everyone can go into breakout rooms for 7 minutes, 5 to 7 minutes, and let's see how many things you can find in this chart. Write down everything you can learn from this chart. So can we get them into breakout rooms?
Yes.
So We'll do it. Let's do it for 6 minutes. Everything you can learn from this chart.
So we are going to have a breakout room.
Yeah, one moment, please.
So everyone will click the joy, right?
Say again.
I think
Okay.
our team, yeah, has arranged. And you click joy.
Hi, Anne. I saw you send the message, right? You mute? Please unmute.
Yeah, they should use the pH chart that I emailed them.
Yeah,
I didn't.
but you text in the main room chat, but now they are in the breakout room, so I don't think they get this message.
Okay, it's fine because they'll pull the one up from the email, I think.
Okay.
Thank you.
Yep.
Oh, there it is. Okay, so I did have it. That's funny. It is here. So we can probably pull them back from the breakout rooms. Let me see if I can do that. I'll give them the 1 minute. Oh, yeah, 56 seconds. Perfect. Thank you. So is everyone back? Okay, so why don't people just call out anything you learned from that chart? Just jump in.
So there are basically 3 types of the pH scale, right? So what I get from this chart is like there are the different type of species there, and there are tolerance. So, and there the range of the tolerance shows that in which tolerance they might live, and if the pH will go down, the death will occur.
Mm-hmm. Thank
So,
you.
Mm-hmm.
Anyone
Bacteria
else?
can survive everywhere. I think. Yeah, probably.
Thank
And
you.
in the last one was written majority of organisms, we think, including human, right? In the bottom, last one was majority of organisms, I think, including human.
So I think the pH of human blood is 7.2 to 7.4. That's in there, yes. Although I try to sway kids away to be thinking about animals that live in the water. But yep, okay. Anyone else?
I have a question. Was it pH of environment where we live, where organisms live, or it's a pH of what?
The pH, so on this
The
on the
pH.
scale. So this is the pH range that organisms can live in.
It's a of environment, right? I mean, for example, if we drink water, and does the pH matters?
So in the United States, or at least here where we live, the pH of our drinking water is 9.2. That's the water. So drinking water standards are very different than water quality standards for fish and other organisms, because chlorine is put in water to kill germs and has fluoride. So humans can ingest like acidic or basic, not very, like orange juice and things like that. And so this is also an important distinction to make with students, that everything on this chart is related to organisms living in water, so not people. Any other observations anyone wants to share?
Yep. From the chart, the student will know that there are 3 kind: acid, basic, and also net neutral, from the range from 0 to 14. So they know the quantitative range in pH measurement. So this information that a student will get at the first, and then there is a kind of color range I'm sure that the student will ask, what is that? Is this kind of from indicator? What is the color that will show in pH 0 until 14? And then that's the pH rate that the organism in the water can live or survive. When it's less or more, it will be problems. Thank you.
And so I'm going to share my screen again. And this is what you're missing. Can you see this part?
Yes, we miss in the PowerPoint that sent to us. Yeah.
And for some reason, when I go to full screen, it's not there. I don't know why, but you can see right here. I know at least in the United States, these are our water quality standards for fish and freshwater organisms. And they can see, they get an introduction that 6.5 to 7.5 is the best. It's excellent. And that's down here where most organisms can live. Also, it introduces the idea that for pH, we know 7 is neutral, right? And below 7 and above 7, acidic or basic. But for organisms, 6 to 8 is considered the neutral zone, because we can talk about the exponential scale, which we do later, but not right now, in terms of from 7 to 6 and from 7 to 8 is not that much more powerful, versus as you get much lower and much higher, right, organisms start to die. So with kids, they share, different groups share and point out things that some people haven't seen, but then
Excuse me, Anne. Sorry
Yes.
for interrupting, but I have a questions because my background is not a chemist. So my question is related to the arrow, the line and the arrow. You use a double arrow because in mathematics, when we have a number line and there is an arrow, it means that it will increase and decrease. Does
Yeah.
the pH also have the similar meaning?
So I think that that's a mistake. It should cut off at 0 and 14. Do you agree?
Okay.
Should not have those arrows.
That's
Okay,
correct.
thank you.
Yeah, so I should redo all of that. Thank you for noticing that. Okay.
My pleasure.
So, do you have other questions?
No, thank you.
So what students often get from this is that the pH measures if the stream is going to be acidic, basic, or neutral. They notice that most organisms need this neutral pH, and as it starts to go one way or the other, then organisms start to die. And they can see right away 6.5 to 7.5 is the best. They can also see like this neutral zone, and then they really do see that bacteria can live in that huge range. And then they also notice that plants, we go back, that plants actually can live in this basic range. Okay.
And I have questions.
Yes.
Yeah, Dr. M. Do you have any experience when the students, when you implement this lesson, they ask about pH and then what is the P and H, and do you, as a teacher, should you explain to them power of hydrogen and something like that? Thank you.
So they do ask that. And so the way I approach it is I want the students first to experience different products and learn more about that. And then after, we do go and we explain the pH scale and how it works, and what pH stands for. So we do talk a little bit about that to give them more context. But we wait until after we've done some experiments, so that they don't start confusing things. But yes, we do that a little bit, not at a level of high school chemistry, but just, yes.
Okay.
So then I say to them, we could actually go out to the stream right now, and we could test the pH right now. And what will we know if we go out and so I use a pH probe. The probe is going to give me a number, or if you use pH paper, right? So we could do that right now. And we're going to know what it means, right? the kids say, yeah, we can use this scale. We can see what's going to live there, right? So what is it that we won't know though? Any ideas? So we'll know in terms of what range of organisms can live. If we went out now and we got a neutral pH, we should, we should feel happy. But what is it that we won't know? And if you have an idea, and you're just going to have to call it out. This is really a hard one for 7th grade too. What won't we know?
Yeah, I think they want to know a little bit about the quality of their stream by measuring the go to the stream and then measuring the pH.
Mm-hmm. So that's what they say, right? They want to go to the stream, they want to measure the pH, and they'll know if it's healthy or not because they have this chart that can be useful. But what is it that they won't know?
Maybe the things that they used to measure, indicator or something, because they don't know before the investigation.
Okay.
Yeah, the
Well,
paper.
It's a hard question, not only for 7th grade, I think.
Yeah. So how will we know why we got that number, right? So we'll go out, we'll get a pH number, we can use this chart, but we won't know why we got that number, right? So what we want to do in class is figure out what can we do in class that will give us some insight into the number we get out at the stream. So does anyone have any idea of what experiment we could conduct in class that would give us some insight? Now, my students say, oh, we can go get a bucket of stream water and test it. I said, well, but we're going to do that at the stream, or we can, but we'll still get a number and we don't know why we got that number. So do any of you have any ideas of what we could do? And usually I break them up in small groups to just talk for 1 minute. Anyone have any ideas? That's how my students are. They have no ideas. So I said, well, what if we go out there and we get a very high number? How will we know? Or if we get a very low number, how will we know? Now, think about the contextualizing activities we did. In particular, that chart where we circled point and non-point source pollutants. Anyone have any other ideas? So I might have a student say, I have an idea, let's test lemons and orange juice and Coke. I was like, okay, why would we want to do that? And they're like, I don't know, this would be fun. Okay. I said, but is there something we might want to test? Okay, anyone have any ideas? Any of you? Okay, so I say what?
Just test the water from the school, that the water in the schools, and then compare with the water from our home, for example.
Okay, so this is a comment also that I get that's a very nice jump start. So students will say, let's test the drinking water from our drinking water, and let's test the water in the sink in the science room, and then that can help us. Okay. And one thing I say is to help students distinguish between the drinking water in our school goes down the drain and it goes to a wastewater treatment plant. So it doesn't impact outside, except it does, but we'll get to that in a minute. But then we can move from that conversation about testing our water in school to what about testing everyday products that people use outside that can get into the stream in large quantities. So everyday products that can get into the stream in large quantities. Can we just generate a list? So what are some products in your countries that are used outside that might get into streams? You want to just call out?
Detergent.
I'm sorry, say that again.
Detergent.
Detergent.
Soap.
Yeah. Shampoo.
Do you understand that?
Detergent. Soap.
Shop.
Yeah. Soap.
Yeah.
Oh, soap.
Yes. Shampoo.
Yes, soap, Annie.
Mm-hmm.
It's in the chat.
Oh, I don't have my chat on. Fertilizer. My kids will come up with this stuff. Fertilizer.
Perfume in the chat.
Okay, you can help me. Anything else?
Raindrops.
Say that again. And you can put it in the chat too. So whoever just shared, will you share that again, please? What can get into the stream in large quantity? And it can be products and it can be other substances. So my kids come up with stuff like this. They'll say soil, dog
Oil.
poop, car oil.
Oils in the chat.
They'll say
Non-domestic waste is in the chat.
what's non-domestic waste? Can we clarify that?
Used cooking oil is in the chat. Oil, garbage, plastic. Home waste. Home waste. Garbage leach.
Okay, that's a good list. So every group, every class comes up with a list, and then we go through this list and we say what is feasible. And well, they'll say pesticides. And what is feasible and what isn't feasible in terms of two criteria: safety, but also thinking what can be in there in really large quantities. So detergent, we would have to clarify. If you're using it in the house to wash clothes, then it's, unless there's a pipe that breaks, that hopefully that won't get into the stream. Lots of different soaps can get into the stream because people outside wash their cars, they wash their decks, they wash their garbage cans, they wash their windows. So someone might say, oh, what about Windex? We would look at fertilizer and everyone said, oh yeah, fertilizer, large quantities. And then perfume soil would go down the list. So then the next question becomes, how can we test these? So what are we going to do? So I provide students, I'm going to unshare this, and I'm going to share something else. Okay, can you see this? See if I can make it bigger. Okay. This is also something I sent you. One of the practices of scientists is to design and carry out experiments. And I want my students to experience that. So I say, usually you walk into a science room and a teacher has already set up materials for you to do an experiment. And then you read the directions and you do the experiment. I said, well, somebody thought of that experiment, somebody designed that experiment, and someone wrote the directions. So that's what they're going to do. So I just say a famous science book publisher has hired you to design and write a lab setup and a procedure for conducting a lab that investigates the pH of various substances that can get into streams. And it's got to be in large quantities. In addition, she wants you to create a data table where students will record their data. So there's several parts to this. The left side is the lab setup. Those are directions to teachers. I have students write down their initial ideas on what we can do for an experiment. We share ideas, and then together we create a lab setup. And then how students should conduct the experiment, we create that. On the back side, they draw their ideas for a data table. We call it a sloppy copy data table, just like what should go into a data table. And then we spend time creating this experiment. So I'd like us to go back into breakout rooms just for 5 minutes and see what ideas. And so this is where we talk about first their initial ideas. They don't know. They'll say, let's throw a bunch of chemicals together and test them. Some will say, you know, they have very few ideas. And we talk about, you know, controlling variables, and what are those variables we can control, right? How to design an experiment, what's a fair test. So if you can go into breakout rooms for 5 minutes and just come up with some ideas on how we're going to test and specifics in terms of how to set up. So this would be a directions just to the teacher right now. They would not the procedure, but if you can just focus on the directions to the teacher, see what you might come up with. And you can approach it as a middle schooler if you like, or you can approach it just as adults, up to you. So can you create breakout rooms? Who's doing the breakout rooms?
Yeah, Mongkon will help doing that.
Okay, so see if you can get a procedure just to set up the experiment, not to test.
And you will share the PowerPoint later, right?
And ไปห้องไหนนะไม่แน่ใจนะ
อยู่ห้อง6ครับ
อ๋อโอเคโอเค
I'm sorry. I wanted to ask, can you repeat the task, what we should do in breakout rooms?
Actually, I'll try to put you in some of the room.
Oh, I know my room. So in the breakout rooms, we
Oh, they
all
need a
of
password?
us.
Really?
No. I mean, I know my breakout rooms, but all of my teammates maybe not understand the task. What should we do in a breakout rooms? Just you don't have a voice. I mean, it's switched off. Yeah.
Okay. So we're trying to figure out how the teacher should set up the experiment specifically.
Yeah, okay.
So in terms of materials and what they should do. And let me, I think I can write a note to everyone that way. Does that make sense? Does that make sense to you?
Yeah, I understand.
Okay. How do you say your name? Buren?
Darren.
Baron?
Yeah, Darren. Yeah. Daryn, Darren.
A-A-R. Oh, but it's B-U-R-I-N. But it's
Yeah,
Baron?
that is Burin. This is
Okay.
that was Darren from Kazakhstan.
Oh. Right,
Yeah.
okay.
Yeah, Daryn. Darren. I think they might not be used to to assign the students to design their own lab.
Right.
Yeah,
That's I was trying to take this a little more slowly because it's a new idea.
but I think it's a challenging one, right? To that thing about that
So
yeah
we could
that they might challenge, but it's also we can ask them what do they think? Is it any scaffolding do they need to provide for students?
Well, the students are usually in the dark, but I just wanted to see what they came up with, and then I'll share what students come up with.
Yeah, that's right. And maybe maybe we can ask them what do they think that from their classroom can students can be able to do this, or maybe any scaffolding strategies that can help them, something like that.
We'll ask them.
Yeah.
But this is hard for students because they've never done it either.
Yeah, but in your classroom, but that is the kind of tasks that they are assigned to, am I right?
Yes.
Yeah, that they can design their own investigation procedures on their own lab.
For the PH one we do, we kind of step through, but I first want to see what they can do. And I always have a couple students who kind of have great ideas. Oh, we should get different containers and put substances in them. And some will like be clueless. But it helps those stronger students to stretch, and then the weaker students then also get insight. So in groups, it really helps. And then there are some people like, they, until we start actually throwing out ideas together, then it starts to make sense to them.
Yeah.
But I have students who say, we don't know. Did I give him a time? I don't know the time, because this one can be a tough one.
We'll go to check. Yeah, that meeting room, that breakout room, they know what to do.
Excuse me, may I ask, are we coming back from the breakout rooms? I see, okay, thank you.
Mhm.
Would you like to call everyone back, Anne, or you will like?
I already did.
Okay.
Okay. Okay, so this is an activity that's very challenging for students and maybe everyone because we just aren't used to designing. And then we have to help guide them on a middle school level. So do we have a couple people who just want to share ideas from your group? And if you do, just you got to jump in and share what you came up with. Any volunteers?
Yeah, in our group, we just discussed that the experiment that have to be run by the teachers and followed by the students is to prepare the because the student want to know how to measure the pH, and also the instructions told them to measure any substances that probably go to stream. Then I think that we think that the teacher have to prepare one control water. It's not mineral water, but maybe aqueous that should be natural, show the natural pH. And then there is also water with high acidity, and water with high what is it, alkaline. But contextually, the stream water, I mean the garbage or oil or anything, will go together in our stream water. If the students just measure that, then they do not know what is it, they do not know what substances make the water pH higher and lower. So that's why we think that we have to try to introduce them which substances will make the water more acid or more alkaline, and also compare to the natural water.
Mm-hmm. Okay, thank you. Anyone else want to share?
Yes, adding the answer or explanation from Dr. Murni said before, for the initial ideas, that's we think the student is, this is the middle school student, right? So we think the initial ideas is to scaffold the student how to measure or compare the stream of the pH, what the apparatus that can that they can use to identify or to different the pH scale.
Mm-hmm. Okay, maybe one more.
Okay, so for hi. So for my group, we discuss that we want to help the student to understand the level of pH that suits every plants. So by using control and the same as Madam Morni said just now, the idea is the same. But the how we want to control it, it will be discussed furthermore later on. That's all from us.
Okay, thank you. All three good ideas. So can you see the sheet?
Yes.
So what we would hope for students to come up with in terms of directions to the teacher is this idea of a control for sure. But when we set up our experiments, we want to make sure we control a few things. We want to have the same amount of each substance. Some of our substance, well, so we use a pH probe, and for pH paper, the products have to be in solution, right? So we talk to students what in solution means, and then can we put, for example, dry fertilizer into tap water, because tap water has a pH. So someone, figures out distilled water, right? So the same amount of each substance and the same amount of distilled water. We want to make sure that we have containers for each substance, because some students think we should put everything in one container and test the pH. So we have containers for each substance. We want to make sure that they're clean, right? Because we don't want to contaminate anything. And then we test around 15 substances, 15 to 18. And so when we create a lab setup, what we decide is our container is going to be tennis cans, because we have sports right at our school, so we can get tennis cans easily. So we're going to have tennis cans, clean tennis cans, and we're going to put 500 milliliters of distilled water. And then the question becomes how much? And so we have a conversation with students, how much. Some things are already in solution, like Windex. So you don't need to do anything with it. But some aren't, like fertilizer. Students want to test soil, etc. And so the question is how much, and we have students talk about how much they want to test. And we can get into conversations about concentration, which we actually do later on when we look at distilled solids. But oftentimes students will say anywhere from like 100 milliliters, they have a container, to like 250 milliliters, which is a huge amount, but they don't know that yet. Okay, so we create this lab, and we want to control everything except for the different substance. And then we talk about students setting up the procedure, and then I have them create a data table. Most often their data tables have the name of the substance and the pH, but I like to have the name of the substance, the prediction, both for the number and for the if it's an acid, base, or neutral, right? And then the actual number, and if it's acid, base, or neutral, because then they get practice with the pH scale. And so we end up really with something like this. Let me find my document again. Sorry about that. Why can't I, okay, I gotta unshare. How do you unshare?
Go back to your screen.
Here?
Go back to your main screen and then pick unshare.
Okay, sorry about this. Okay, that's not the one I want. Okay, so we end up looking at what is the pH of various substances that can get into the streams in large quantity. And we've created this experiment that's going to look like this. And let me show you, right? So we take tennis cans. It's got 500 milliliters of, this is windshield wiper fluid. And this particular class wanted, they had 200 milliliters of everything that didn't dissolve. So this is Miracle-Gro as a fertilizer. So they had 500 milliliters of distilled water, and then we put in a container that had 200 milliliters of fertilizer. So we end up with all these substances that they can test, and they're in large quantities. And I set up the lab. They don't set up the lab, but we help conceptualize the lab, right? And then they have to decide that when they conduct the lab, we're going to use a probe, and then they have to make sure the probe is clean. Let me grab a probe. They have to make sure that the lab is clean. And you can just put this in the chat. Would you find this useful for me to show you this? Or I don't know, like how many of you would be able to use a pH probe if you'd use pH paper. So do you want to just quick throw in the lab or put a thumbs up or not? I'm happy to show this to you. But what we do is we test all these substances. We test all these substances in class after I follow their directions to set it up. I have just a picture here. I have these containers from like a fast food restaurant that I use so that they don't spill. And then we test the pH. Students go test the pH and then rinse it off, and they test the pH. And now they have a good sense of what the pH is of substances that can actually get into the stream in large quantities. Do we have any response in terms of testing or not?
I don't see any.
Oh, by the way, Anne, did you also introduce about repetition of the experiment to the students, or they just measure their pH once?
So when we talk about the student procedure, we do talk about that. So they're going to test it 3 times to make sure the probe is working. So I tell them, like, they're in charge of the technology isn't in charge of you. So if you put it in a substance and you get 10.5, and then you put it in again and you get 3.2, and then the third time you get 7, something's wrong, right? So you have to see if you need to fix something, etc. But they're going to test it 3 times, you know, so if it's 10.4, 10.5, 10.3, then they can feel confident, and then they'll put the average, they'll record the average. And one thing we always do, whether it's like this in-class experiment or when we go out to the stream, we always share all of the data to see if there's outliers, to see if some of the equipment isn't working, if there is an outlier, to see if it makes sense, or to see if there's an issue. But we can see in the curriculum, yeah, that they're going to do it 3 times. So then they test everything in class. So the pH lesson goes a little slower, first because they don't know what pH is, but second, we want them to have some design opportunity. So they design the experiment. And third, now they have a good sense of the pH of lots of things that could get into the stream. So in Michigan, where I'm from, windshield wiper fluid is just used a ton in the winter. And so it has to get into the stream in large quantities. Fortunately, the pH of windshield wiper fluid is very low. I mean, sorry, is neutral, right? So we can at least be rest assured in terms of pH, that if windshield wiper fluid gets into the stream, it's not going to impact organisms. On the other hand, we start looking for patterns, and it turns out that most cleaning supplies are basic. So if we go out to the stream and we have a basic pH, will we know exactly what's in there? No, but it's important for us to collect data of observations, right? So we want to look to see if we see soap, or do we see lots of cars in the neighborhood, or do we see lots of windows? So do we see nice lawns, and then we get numbers that are similar to fertilizer, right? So now not only will we be able to get a number at the stream, but we're also going to be able to have some context.
And there's a question in the Zoom. They want to know if they're going to do the experiment by group or individual.
So on the experiment, we always, so we use a program called SparkView. You can get it on the phone, you can get it on an iPad. And so I set these up on different tables, and students create a nice data sheet. And then I have groups of students go around and they test the products, and hopefully they get them all tested. If they don't get them all tested, we're going to share the data. But yeah, they're working in groups to test. And their predictions, I mean, they're always mostly guessing their predictions, but they're usually way off. It's definitely a really, I have found to be a very important experiment. And then we can use the same substances later on when we test for dissolved substances. We don't test things like car oil because I don't think they have a pH, right? And it ruins the probe. We don't test things like gasoline. What? No, yeah, we don't test things like dog poop. We said like we can't test that. We also don't test things like plastics because the probe will only work in solution, and plastics don't go in solution. But we could, test stuff and put it in there and then see. If we test soil, soil usually is neutral because soil doesn't dissolve unless something is in the soil. Another question?
Yes, there's a question in the Zoom that says, I'm sorry, in the chat that says, what is the outtake for students testing some of the chemicals such as wiper fluid?
What do you mean by the outtake?
I think the reason.
Why do we test windshield wiper fluid? That?
I think that's what the person.
So we're trying to test everything that could get into the stream in large quantities, and windshield wiper fluid in the United States and Michigan.
What do they learn? So the thing is, what do they learn and why they need to test it?
So they can end up categorizing of the 15 or 18 things we test, which ones fall into are acidic, which one's basic, and which one's neutral. And then if they get into the stream in large quantities, which organisms then could end up not being able to live. So one follow-up from this activity is for students to write an explanation based on one product that we can talk about next time after you work with claim evidence and reasoning. But the other thing too is because of things will dissolve in the water, right? And concentration is another conversation to have. But what it'll allow students to do at least is to say, okay, if we have a basic pH at our stream, here are some substances we can rule out because we know they're acidic, or vice versa. And then it also leads to a nice conversation about buffers, which we'll talk about in a minute. But if students get a basic pH and they see soap suds, then they can be thinking, okay, what happened in the neighborhood, in the area, in terms of potential cleaning supplies that could have gotten into our stream. So the emphasis on what people do on the land really impacts what happens in the water. So when we're asking, is the stream acidic or basic or neutral? Now students have a little sense of what the pH means in terms of water quality. They don't understand the pH scale yet, but also what happens when pH becomes more acidic or basic. And then we have a student reader that helps with that. And then the important ideas so far, so hopefully we're at a point now where students understand that people use products outside on the land. And because of runoff and storm drains, that storm drains are connected to waterways, and anything that runs down a watershed can get into bodies of water. And that most organisms need a neutral pH, and that organisms start to die as the stream becomes more acidic or basic. And that they know bacteria can live in this really large range. And then we introduced this idea of riparian buffers. And a riparian buffer is any kind of vegetation, bushes, trees, shrubs, grass that can absorb chemicals. And plants, can live in this range, in a basic range. So the plants can actually absorb a lot of those cleaning supplies before they could get to a stream. And then there's stream buffers, like if it has limestone or some geological rocks and things that can also help neutralize the pH. So that in nature, there are ways that streams can kind of take care of themselves. Unfortunately, people's actions on the land often go over the limit of what a buffer can handle. But these are some ideas that are also in the reader. So
Pardon me, Dr. N.
I'm sorry.
Okay. I have a questions. Before we discuss about the buffer here, is there any question from your student that asked to you what is something quote unquote in the water that make the water is acidic or a base? And is there any question that student asked to you why the range is from 1 until 14 maybe?
So they do ask about this. And we do, after we collect the data from the stream, then we do spend time explaining how the pH scale works and that it's exponential. And we try to do that on a middle school level. They're familiar with exponents, but we wait until after we collect the data before we do talk about that. And then they can see, because of the exponential nature of the scale, how it becomes so much more powerful as you go to the higher or the lower numbers. Did that answer your question?
Yes, for the first question, if there are a student asked to you that what is some things that make the water is acid or a base? Is there any such a question from the student?
In terms of what would cause it to become acidic or basic? So that's where the products come in, right? Because the everyday products people use on the land. So we test 2 fertilizers. One is very acidic. It's like 3.8 for the fertilizer, right? And one is more neutral, right? And so we try to test 3 different ones because there are some fertilizers that are basic, right? So one thing we're also trying to empower students is what action steps can people, including themselves and their families, do on the land that will help to prevent streams from becoming acidic or basic. So when we test the chemicals, the everyday products, we're trying to help kids think about the products they purchase and what they do outside on the land. So I tease the students. I say, no one goes to the grocery store and says, okay, here's the list of pollutants I'm buying today. We go to the grocery store and we say, okay, here's the products I need to buy, but we don't understand how they can impact waterways when we're outside. So that's why the testing of the products that can get into the stream in large quantities, right? So we're not going to test Coca-Cola, but things that can really get in large quantities and change the pH are the things we want to test. So did that answer it?
Yes, thank you very much.
Okay. So before we go outside, we always write predictions, and we use the same format every time, 4 parts. So they're going to predict a number, okay, and connect it with the text, right? So if they predict it's going to be 8.5, they need to say that's basic. Then a standard, excellent, good, fair, or poor. And I guess I didn't talk about the standard. So probably 35 years ago, a group of scientists, science educators, we like water chemists, water biologists, they got together and they created what we have in the United States are national water quality standards. And do you have things like that in your countries?
Yes, we have in Indonesia.
Okay, right. And so excellent, of course, is the best, but good is also positive. So anytime it falls in a standard of excellent or good, we're going happy with our results. And fair or poor means there's a problem. And excellent, good, fair, and poor goes with every water quality test. And so you always know if it's excellent or good, that's positive. It's fair or poor, there's a problem. And then each water quality test, of course, has different units or numbers. And so their standard has to match up. So if they were going to say 8.5, that would be fair or poor, I can't remember. And then they need a statement about types of organisms that could live. So if they said it was going to be excellent, then they would say that all organisms could live. Or if it was going to be good, that many, and some or few, that all of these need to match. And they can be completely wrong in their prediction. It's a prediction as long as what they're saying matches up. So if they're going to say 8.5, they can't say it's going to be acidic, right? If they're going to say 8.5, they can't say it's excellent, or they can't say all. So this gives them practice and experience both with the pH scale, right? And then understanding in terms of organisms. So it's just it's a subtle way for them to make sure they are understanding what the numbers mean in terms of acidic or basic or neutral, how it connects with the standard, and then how it connects with organisms. Then they also need at least one reason for their prediction. So that's going to tie them in again with the science ideas, right? Do they think, so all of these have to match up, right, for their predictions. So it's going to be for every single water quality test based on that test. Erase that. Okay, where's my array?
They also said they have water quality tests in Malaysia.
Awesome. Okay, so then we go out and test. And how come I can't do this? Okay, so we asked now, is our stream acidic, basic, or neutral? This a couple of years we've gone out, this is a gigantic soap suds pile. These are 2 7th grade students. This is from 2 years ago during COVID, so everyone's masked up. But we have storm drains that empty right into our stream. And this was fairly close to the storm drains, but not right next to them. And we had piles of soap. So it was great it was unfortunate for the water quality, but it was great for students because they tested the stream, they got basic results, and they could connect it right away to soap suds. And then, they have to try to figure out where those soap suds came from. So they could then go back to the pH lab and take a look at everything that was tested, and they could narrow it to soaps. Like it could be car wash soap. It could be people cleaning garbage cans with this product or that product, right? So they could narrow down what they think would be the reason why they got their numbers. We'll talk about explanations either next time or the time after you work with Joe on explanations. And then action steps, right? So this is very important to me because I want students to use their science. So what are some actions that we can take outside to prevent our waterways from becoming acidic or basic? And I have my students write action steps even if the stream is neutral, because I think we've tested for 28 years, and in only 2 years, we had basic results. Otherwise, we had very neutral results. And in both the years we had basic results, we could see there were soap suds. And so action steps include things like, choosing products that are neutral, and they can be very specific about that, but can also be making sure to plant buffer zones around your yard, or not to cut down trees and bushes around waterways, making, rain gardens so that, water flows into them, right? So there's a lot of action steps. And then we go back and say, okay, can we answer the driving question now? We can answer part of the question. Usually we know the stream is healthy related to pH, right? But it's only one piece of the puzzle. We go back to that driving question board, all the questions on pH now, we can see if we can answer. Some we can't answer yet because we have to, some questions are like, what is pH? What does the P and the H stand for, and how does the pH scale work? But we can go back and, we can go back and be able to answer a lot of their questions. So it's, again, really affirming to students, and then it helps to continue having them be engaged in class. And then we ask, are there any new questions to put up? So we're always trying to go back to the driving question, which is the health of the stream, and then see if new questions come up that we can add that we might answer later. So yeah, after you talk with Joe, we'll look at explanations for this. But what I want to do now is I just want to take a look at lesson 3 in the materials, just to show you how it works. Sorry, Joe keeps telling me I'm talking too fast, and so please don't hesitate to just jump in sometimes and say, and slow down. Okay, so let me.
Excuse me, and there's a question in the chat box.
Was there a question, Joe, in the chat box?
Yes, it just came up. How long the learning takes? Is it project-based learning?
So it is project-based learning because we have a driving question, which is how healthy is our stream and how do our actions impact? So if you look at all the features of project-based learning, so a driving question, we contextualize learning, we have students engage in investigation and have them plan, they plan and carry out investigations you see in the pH. They, in this case, are able to collect real data in real time, and they're going to analyze that data and synthesize it as they create a scientific explanation. That's the artifact they're building, is the explanation. They'll also going to create models as they get more evidence for different water quality tests. What are the other features of PBL?
Collaboration.
Oh yeah, there's a huge amount of collaboration. Students are always working together to try to figure out, to solve. Teacher works as a co-collaborator. So like my role as a teacher is to guide, to support, when they get stuck. I intentionally like how to organize an experiment for pH. This is really challenging for students. Most students have never done anything like that. And so it doesn't mean it's too hard for them, so I don't do it. It means that I work to really help them figure it out. And I know that some students, it will make perfect sense. Other students it will be messy and they'll struggle for a while and they'll get it. And then there are some students who will definitely learn, but it'll still be challenging for them. Any other features of PBL?
I think we're good.
Okay, so yes, it is project-based learning.
Variety.
It's a variety of project-based learning. You can jump in, Joe. Jump in. Did that answer your question? Okay, so
I would say it's an excellent.
I'll mute myself.
You have to mute yourself. I would say it's an I'll talk to you. I would.
Both of you is muted.
Okay, start over.
I would say it's an excellent example of one type of project-based learning, right? So what we've tried to do is to make sure teachers from a variety of different contexts can actually use the materials. So in that sense, it's more structured than if you would just design your own unit, but it allows kids to pursue their learning, trying to answer a question. And in answering that question, they have to experience phenomena, they have to do investigations, they create products, they work together in collaborative teams, they use technology tools or various kind of tools to sort of find to provide a response to that question. So I would say in that sense, this is a really excellent unit of a project-based learning unit that can actually travel in different contexts. Like, for instance, this particular context, we have people from Thailand, we have people from Malaysia, we have people from Kazakhstan. So there are a variety of different places we can use this, right? You need to contextualize it a little bit better for your particular environment, but outside of that, it's a really nice example because of the engagement that kids have as a project-based learning unit.
And I'm seeing we only have a couple minutes left. So I'm going to just quickly, because you can look through the unit, but I just want to show, since we've kind of walked through the PH. So there's the question and then a quick overview for teachers. Here it shows what learning performances are based on the three-dimensional learning and the NGSS from the United States. There are safety guidelines. It talks about preparation and then materials for the teacher for the various groups. And then these are all the individual handouts. So teachers can just click on them and then they will come up. There's some background here for teachers to help them learn if they're unfamiliar with pH, and then exploring pH and designing the experiment. There's also some optional ideas for teachers who might have more time, and optional activities. And then after reading, again, some more background, and then tells you the purpose of the activity, and here's some ideas for homework. These are some of the science ideas. And then in the yellow here, right, some suggestions or notes or things. Again, teaching strategies, helping to make it accessible to all learners. And then, so talks about the logarithmic scale a little bit. There's the sheet with I need to get the arrows off, and then water quality standards. So it steps the teacher through. Here it talks about pH tools and various options where teachers can get materials or what they can use. And then again, so it's very educative materials. Teachers could use it step by step, adapt it to what makes sense for them, modify it however they need to. But everything is in here, right? How to brainstorm ideas. So a lab setup. So, and then different options on recording data, ending the lesson. So, so that's day 1, day 2. So it goes through each of several days to explain, so when you were asking about how many trials, so this is a pH data table that students could come up with, right? So a prediction, and then what it means. They test the results. Okay, so kind of everything here is spelled out for teachers for all the different activities. And then the explanation stuff we'll do, we'll do another time. Let's see, how does that end? Yeah. So just so you get a quick sense in terms of how the unit is set up. I know we've kind of gone slowly through the pH one, and it's the one that does take the longest because kids don't have really any context. Then the other water quality tests will go much, much faster after this, the background and things. Yeah. Well, thank you, everyone, especially on a Saturday evening. Spend your time. I would welcome any feedback. If you want to email me if you have feedback for today on ways I could improve and make things better for the next ones, I would welcome that. So,
and I believe we are meeting on Monday to again at the same time, your evening and my morning, to begin our work on explanations and then talk about modeling.
Yes. Yeah, we use the same link.
Yes, we'll use the same link.
Yeah.
Thank you
Okay.
very much again for the workshop and clarifying the unit. Thank you.
Are there any other last questions?
Yeah. I just thinking about the last part of the presentation is about the action of the student have to take if they want to contribute to reduce the pollution of the stream, their stream. So did you also ask the student to check the ingredients of, for example, because you mentioned that the student have to choose what kind of product that they will buy for daily consumption. Did you also ask the student to check the ingredients of the, for example, detergents or soap or shampoo or anything that will be go to the stream? Then they will decide which one is better or which one is more environmentally friendly for the water.
So thank you for that question. I have a cart in my room that has all the products that we test so that we can check their ingredients, and especially when we look for dissolved solids, and we're going to test nitrates and phosphates so that they can look at the ingredient list. Another thing we test is tap water, because even though for us it's used inside, so many people in the neighborhood have sprinkler systems that are also tap water. And tap water in Michigan is 9.2. It can get into the stream in large quantities. But yes, they can check the ingredients. The other thing, I think one of the main takeaways for the action steps that they know they can apply is if they wash their cars or if they wash garbage cans or anything outside, to do it on the grass, because it won't go down storm drains, and grass can live in a higher basic pH, and that's what cleaning supplies are. And the biggest action step are the car wash and riparian buffers, right? So that they know that they can plant trees and grass, and that will help. But yes, the checking the ingredients is really important. Although sometimes the ingredients, it says this product is very earth friendly, and then we test the pH and it isn't. So those are, you cannot always trust what labels tell you, is something that they tend to learn as well.
Yeah, thank you, Anne.
Okay, so thank you everyone for participating in your late Saturday night. So we appreciate it, and yeah, we hope that you benefit and learn and enjoy this session, and we will see you again on Monday night, same time, same place, the same Zoom link. Okay, so yeah, with Professor Joe, yeah, on modeling.
No, we're gonna
Yeah.
first do
Oh,
explanations because Anne needs that more. So
okay.
we'll first
So
work on writing scientific explanations, and then we'll doing modeling on Monday and Tuesday.
okay, yeah,
I will stay on for a couple minutes if anyone has questions.
yeah. So on 27, if it's Bangkok time, it's 7 p.m. same time. Yeah.
Well, have a nice evening, everyone.
Yeah, thank you,
Yeah.
Anne.
Yeah, thank you.
Thank you.
Dr. Kasara, thank you.
Yeah,
Have a
thank
good
you,
evening.
everyone. Yeah, bye-bye.
Bye.
Good weekend. Bye-bye.
Bye.